that's the table of contents for today. So as opposed to Monday, we're going to focus on stabilization and training issues and practices for GANs. We'll start with a little recap though. So Monday we saw what a GAN is, how it works, and what you can do with it. So what is it? It's at training, it's a couple of networks, a generator that tries to produce samples that are drawn from a target distribution, and a discriminator that plays the role of a loss function that's going to distinguish the generated and the real examples. And you train both adversarially. So yeah, how do they work? The discriminator calculates divergence and tries to maximize it, while the generator tries to minimize it. And if we restrict ourselves to what you've already seen, if you were to build a GAN, the way you would do it is you define a generator whose input is a random input of a dimension that you precise, and it's you make it so that it's going to produce an image, for example, of the dimension that you desire. You also define a discriminator network that takes images and produces a scalar. The scalar is meant to be the divergence that we talked about. And to train it, you take batches from the random prior z and batches from the real data, and you pass the z to the generator, generate stuff. The real data passed and this data passed to the discriminator, and then you'd use the gradient descent separately on the generator and the discriminator. Although you could do it jointly if you want, but separately I think it works a little better. That's actually what we're going to focus on today. And I assume you're going to have some code in a recitation that's going to happen, hopefully, because it's. I hope the lecture is clear, but it's bound to remain a little abstract in the end, and it's better if you have some code to look at. If you don't have a recitation, you can find some online too. So what kind of problems can you do with GANs? By default, it's meant to solve generation problems, to draw samples from a distribution. But by extending a bit on that, you can do a bunch of things that we talked about, like conditional generation, or even clustering, or translation from one distribution to another. And pretty much, actually, every task that you'd want to by marginalizing the distribution that you're computing. So they are an extremely powerful tool for generative modeling. They have amazing results that we showed a little bit. It's got tons of potential for further improvements, but we briefly mentioned that they're limited by pragmatic issues that basically mean they have stability problem in training. So let's delve a little bit into those optimization issues. And once we have a little bit of understanding of what's at stake, we'll see a bunch of solutions that have been proposed in the next section. So yeah, GAN training, a lot of things can go wrong, and sometimes it's hard to put a word on what's happening when it's not what you want. But there is a family of problems that happen often that's called mode collapse. So it's easier if we see an example of that. Up. All right, so that's again that tries to generate MNIST examples. And if we advance a little bit, now this is what happens. And you can see that the generated images look okay, but they are not covering at all the entire space. and the more you advance in time, and the more it seems that the only thing generated is 1. So that's kind of a problem. It's sort of a local optimum in the training, I guess, where the generator is only going to focus on a subset of the space that you're trying to generate, and it's going to become very good at this subset, while the discriminator is going to be pretty bad in there, but it's not too bad for it because it's good at everything else. And it's hard to go out of that issue. It's sort of an exploration of the space problem. Another thing, there's a variant of that I don't have a video for, where for example, the generator learns to produce ones, like here, but then the discriminator is gonna, by a reaction, become very good at saying that ones are fake. So the generator is gonna move and try to predict 2s or 8s or something, and the discriminator is gonna follow with a little delay and classify the 8s as wrong, and it's just gonna loop over the entire space and never span the entire thing, but just change the subspace that you're looking at. All of those are generally called mode collapse. Now you've got some errors that don't really fall into that category, that are just extremely weird. Up. Yeah, so that's on Cypher, I think. And if you were to put a word on what's going on here, it's not the same thing as before. It's not producing anything clear. Maybe it's a problem of average. It's trying to predict something that's in the middle. But generally speaking, it's hard to say more than that on what's happening. And as for the cause of what's happening, well, it's hard to put a finger on it. You may argue that the discriminator is too complicated, that it's not complicated enough, so you need to, kind of like when you train your network as you used to, you have to try different things, check your hypothesis on what's going wrong, try reducing the size of something, see if your hypothesis makes sense, tune a bunch of hyperparameters, etc. It's just more difficult here. You can say that the root cause of all of this is the fact that here you're doing simultaneous updates between 2 players as opposed to just training one network. If you're doing that and you want the 2 players to be sort of synchronized in what you tell them to do, and if one learns too fast or too slow, you can have a problem. That's the reason why, generally speaking, the two-player games are not at all guaranteed to converge, and you don't have any of the guarantees that sometimes you may have on simple optimization problem, like convex optimization. We mentioned that there is a stationary point, but you may not reach it. It may not be stable, and just in general, adversarial optimization is much more difficult than single-player optimization, and it's also less thoroughly studied. So you have very little to fall back on. Now you may wonder, if simultaneous updates are this difficult, are we really forced to do them? What would happen if you just train the discriminator until it's very good, and then you train a generator to fool this discriminator? What would you get if you were able to do that? So not even mentioning how hard it would be to get a good discriminator, you can just think about it 1 second. If you have a discriminator fixed, then a generator that tries to fool it is just gonna always output the one point where the discriminator has maximum output. So there must be one point like that, and it's just gonna learn to be fixed, go systematically there and lose all the distribution aspect that we were trying to get. So that's not at all what you want. And if you think, yeah, but if we have the optimal discriminator, the one that's absolutely perfect, and if it's a real image, it's gonna output something, and if it's not, it's gonna output something wrong. But we mentioned last time that the optimal discriminator is one that's gonna emit 0.5 for everything. And so it's the ultimate goal of your training, but in training it's completely useless. It doesn't have any gradients or anything. So basically, optimal discriminator only is a sentence that only makes sense if you're talking relatively to the generator. So you can, obviously the opposite is even more true. The discriminator is there to train the generator, so you cannot train the generator first and the discriminator later. It doesn't make any sense. So you cannot really avoid the fact that you're going to have simultaneous updates. So I said that you need a balance between the two. That's a bit of an abstract word. It's hard to define exactly what it is. But if your discriminator is not good enough, it's not going to give any useful feedback to the generator. If your discriminator is too good, you can, at a high level, you can say it becomes too hard. It's just going to say that everything the generator does is garbage, and so the feedback in terms of gradients is not going to be very useful for you. So you have a lot of problems like that. As of what affects the balance, well, there's pretty much everything. Every hyperparameter you can think of, what optimizer you're using, what learning rates you're using, the architectures of your networks. If you use some regularization like batch norm or dropout, etc. If you decide to use batch norm on the generator, it's going to make the generator hopefully train faster, but then it's going to affect the balance with the discriminator. So you may have a lot of problems that you don't want. There's the number of iterations that you do for each. So far, I sort of implicitly said that you do one time the generator, one time the discriminator. That's not the only way you could do that. You can have a fixed number of, you train you focus on a certain number of iterations on the discriminator and then another different number on the generator, and you can have all the combinations that you want. An interesting idea would be to have those numbers of iterations for each dynamically changed based on some metric, if you were able to compute that metric. Like you could say, I want my discriminator to be always a little further ahead compared to the generator so that it always gets useful feedback, but not too much. So if my discriminator has too low accuracy, I'm going to train it until it gets at least 60%. And when that's done, I start training the generator a little bit until I'm not in that situation anymore. So yeah, everything you've been, you can think of like that has probably been tried. And you can find the papers that are going to tell you if it works or not. I don't know the answer to everything because I don't have the entire list of papers in my name. I just have a few that are going to be in the next section. So we're going to focus on those. Before that, though, you may want to look at what this simultaneous update thing looks like in practice. So we have a toy problem to show you. All right, so that's a problem. So you have a target that's the green point here, and what your generator is producing is the blue point here. So it's just 2D output problem, very simple. And your goal is to have the generator try to produce this specific green point, and the discriminator is something linear that tries to learn that the closer you are to the generator, the bigger your reward is, except it's linear, so it's just going to tell you go in this one direction, and that's the only thing it can do. So let's just take a look at what happens. And you see that in the end it works. But what happened in the middle is that every time the generator was going somewhere, it was going slightly too fast for the discriminator, and so the discriminator direction had to change after the fact, and so you got a ton of oscillations that happens that make the path that your generator point had to follow much longer than the what it should have been, because it was at the solution a bunch of times and it sort of missed the opportunity. So that just give you a general high-level idea of how like hyperparameters could affect the thing. Like if the discriminator was able to learn a little faster or the generator a little slower, you might have gotten the good results in 2 seconds instead of 20. All right. Up. Yeah, so another high-level thing you can look at, as opposed to a GAN player, strictly speaking, is another two-player game. So we're going to take one that you already know, like rock, paper, scissors. So you've played that before, and I assume. And we are wondering if you were to randomly initialize your thing, and you got 3 possible actions that you pick with certain probabilities, and you got 2 players that learn to try to beat the other one. What would happen in practice? So let's say by random initialization, your first player is A is gonna play rock, then B is gonna, if you were doing updates for one after the other, then B is gonna learn to play paper. But when that's done, A is gonna learn to play scissor, and then when B is gonna learn to play rock, and you're gonna get caught into a loop like that. So if you had, if you formalize the problem a little bit, this is the general loss that you have, where if you're trying to get A to be good, you're gonna have the min-max problem, like in a GAN. The global optimum is purely uniform strategy for each of the players. I don't know if it makes sense for you, but from an instinctive perspective, it makes sense, because as long as you have a strategy, there is at least one strategy that can counter it. So the only way to be unbeatable, in a way, is to be completely random and draw each of the 3 things independently with probability 1/3. But if your player B was close to that optimum but not completely there, like one of the rock had 0.4 and the other had 0.3, then A is gonna immediately learn that in order to have a bigger expectation of winning, you need to play paper all of the time, because you got more chances than the B plays rock than anything else. So that's how you're gonna win. So that just illustrates the fact that the global optimum here is not stable at all, because even if one of the players derives a little bit from it, then the entire game learns to something completely different. So if you were to use gradient descent on that, as you'd expect, it's not going to work, and you're going to have a kind of loop of mode collapse, like that. You can see that it does not look like it's going to converge, even though the general optimum was there. But that was with a different strategy that we're going to talk about very soon. So again, the fact that there is a stationary point doesn't mean that the gradients are going to point to it and that you're going to get what you want. The gradients, like we've illustrated last time, they can circle around the point. Sometimes they can point in a completely different direction. If everything's happening how you want, the traditional word for that is saying that the stationary point is a well or basin of attraction. I don't know if you've seen that, if you've done mechanics, probably. one of the takeaways that you can get from that is that the discriminator needs some sort of smoothness that so that it's not gonna go in a very weird direction and tries to like if its weights are not getting too large, you may have, or if its objective does not enforce that the weights go to infinity, then that may partly solve the problems that you get. Do you have any questions so far? Cool. Then we can get into the really interesting part. So we're just gonna introduce a bunch of strategies that exist. None of them is perfect. I'm not vouching that every of them is good, but they are classical, and even though they're not exhaustive, they give you kind of a good panel that's representative of the kind of things that people have been thinking of. And there are many more variations on those on similar ideas. And even though all of them can be debatable, you cannot really argue with the results like we've seen last time. Results are getting better and better, and they're quite fantastic right now. Yeah, I just said that. We're not going to cover everything, but we cover something that's interesting or historically important, and they're not all good. So that's the list of the things we're going to see. You may already have heard of a few of them. WGAN in particular is pretty famous. Now people tend to say, when people tend to say GAN, they usually mean that. So yeah, let's just delve into it. So the first thing people have been thinking of is if you want make the whole process a bit less greedy. Like the entire problems that we mentioned come from the fact that the generator is trying to fold the discriminator as it is now, but it's that might not work at all for the optimal discriminator. And so you're taking greedy decisions that might lead you in a completely wrong direction because of the blinds that the generator has. So instead of trying to optimize the current loss, one idea that these people had is optimize the future loss by doing something that's called unrolling. So what that means is at a certain time step, you compute the discriminator that you're going to get after a few steps of gradient descent. And you're going to find the generator that works, not on the current discriminator, but on that future discriminator. So that means that you're differentiating twice, in a way. I'm just going to formalize that a little bit. Yeah, there's sort of an analogy with chess where you're not thinking of the thing that looks smart now, but you're trying to think ahead. And what if I do that? What is my opponent gonna do? And if you think further, usually you win more often. So there it is. You start with the discriminator at in some state. You compute gradient descent a bunch of times based on the dual objective of the two networks, and you're gonna get this a new discriminator at the time step k plus time step k, capital K. And instead of doing regular gradient descent for the generator, you're gonna compute the gradient descent based on this objective, including the dependency in G over here. So that's what makes this whole thing completely different from just doing k steps for the discriminator and then one for the generator, is that you're differentiating through the gradient descent that you got to get there. So it can give a bit of a headache, but it actually works. Is that clear or not? It's like, yeah.
How exactly is this different from doing k steps for the discriminator and one for the generator?
Well, if you're doing k steps, then you and k and 1, k 1, then you assume that this thing becomes fixed and it does not depend on G anymore. And when you get this objective, you just look at the derivation for the first, like the derivative on the first variables. But here, you're not only differentiating through that, you're also differentiating through that and how changing the generator would have changed the discriminator that you would have got. So it's like this thing has, its total expression is this plus a bunch of things with gradient descent compared to D, and you're differentiating through all of that. So you're gonna, at some point in the expression of this thing, you're gonna have the derivative compared to G of this thing. And that's not something that you have when you just do regular iterations. Maybe it's clearer with a picture. That's called unrolling. I don't think it's specific to GANs, but it's a thing that you can do. So you just compute with SGD a bunch of new discriminators, and then you're gonna unroll in the sense that when you backpropagate, you're gonna backpropagate through all of those SGD steps to get your new generator. That was the technique that was used in the video for rock, paper, scissors to make it converge in the end. So that works. You can see an example for a GAN in the toy settings. So you see that the distribution is just a bunch of clusters that are forming a circle like here. So the down part is what you'd get with a regular GAN, and you can see that there is a kind of mode collapse here where you're generating only one part, like the points that you generate are all in the same area of the image, and you're completely ignoring most of the subspace of the distribution. While with unrolled GANs, you get something that's much nicer and that after a few thousand steps kind of looks like the original distribution. So here's a second idea, both, and like the next one too, having the idea that you just trying to make the entire thing smoother and less greedy. So this time, what they're thinking is, if I update my generator, and after that update, the discriminator has a big gradient, that means that the discriminator knows how to counter the improvement that I just made with my generator. And so I'm gonna get an improvement that's for nothing. So what I want when I update my generator is to do it with a strategy where the discriminator is not gonna know what to do, or in other words, where the discriminator's gradients are gonna be small. So in practice, that means you add a regularization term to your loss, where it's not only the generator loss, but also when you update the generator, you constrain with an L2 term the gradients of the discriminator you would get to be small. Sorry. Yeah.
The gradients of the discriminator are small. The gradients of the generator are also get smaller for the backpropagate.
Not necessarily, because like it's there's the gradient of the discriminators means that the gradients compared to the weights of the discriminator, and that's not the same thing as the thing that backpropagates through the discriminator, and that gives you your feedback for the generator. So that's like a question of going back to what backpropagation is and how it works, but you're not looking at exactly the same thing. So no, it's not the same. You've got derivatives based on W as opposed to the derivatives based on X. In any case, I think the paper is pretty clear, so you can look it up. Here's another paper with a similar idea and a much cooler name. So that's a CMU paper, by the way. So the idea here is kind of the same, but they say if I just train the gradients of the discriminator to be small, where I was, then what I'm going to get is a sort of, at the end of the day, is a sort of peak where the generator is very good at certain points that correspond to normally to the real data that was in your sets. So you learn to overfit on this. And if you want this technique to work better, you need to make the norm of the gradients small, not just as those specific points, but in a region that's around these points. So the regularization term that they use is not just the gradients like here. It's the gradients sampled on, like the expectation of the gradient sampled on the ball that's around that point, plus a bunch of terms that regularize this whole thing. So yeah, I don't remember exactly the motivation for this specific expression, but you get the idea. It's all, again, it's a way of making everything smoother in the hope that it's gonna make the two-player process is gonna work better. Now here you've got another paper. This time the idea is slightly different. Some of the papers that actually have some explanation and understanding on the entire process as a vector field and all the things you'd find in real optimization math paper. And they argue that the process, if you want the stationary point to be attractive, you need, because the gradients are 0 at this specific point, you need to enforce that the gradients of each player for their own parameters is 0. So you're asking the kind of, in the previous paper, you're asking the generator to go in directions where the gradients of the discriminator are going to be small, but on top of that, you also ask the discriminator to do the same thing, try to minimize the gradients of the generator. The idea being, if you were in the situations where the gradients are sort of a circle around the stationary point, this is the small push in the right direction that's going to make the gradients point toward the center. It's a little tricky. And in particular, it's got one big problem, which is that they call that a consensus objective. So it forces you to go to a stationary point, but stationary points are not necessarily minimums. They can also be saddle points and maximas and a lot of things. So if you add too much of this technique, it's probably gonna make you go in a completely off direction. So it's usually the lambda term that they use here is a little bit. So yeah, they call that consensus because it sort of means that if you want the two-player game to work, each player has to take into account that the other exists. So they are not thinking so much in terms of adversaries than in terms of two people having a different side of the vision and trying to go to the same point. It's a slightly different perspective. It's a little hard to think of. And mainly it differs from the previous ones because in the previous ones we were just affecting the discriminator, and they think of the process as two players and take that into account. And apparently it works. Yeah, so you can kind of get an illustration of what it looks like, and if you're interested in the general idea, you can look at that page. So that's the kind what you call a non-conservative field, which has to do with the overall value of the gradients around a ball that surrounds your region. You don't have to know the details. And so that's basically what happens in a GAN without supervision, where you've got a bunch of saddle points and you've got a bunch of equilibria, and it's not very clear where the gradients are pointing. In a completely generative field, the conservative field, the gradients are all kind of collinear and pointing toward the equilibrium points. And if you just combine a little bit the two, you get a situation where the gradients tend to point toward where you want to go, or even though it's not perfect, but you can still backpropagate through that. Right, we are done with this kind of techniques. We're moving on to something that might be a little more representative of what your average GAN paper looks like. So that's people that had a bunch of ideas of, yeah, this regularization technique might work, and they just try all of them, and then they try to combine them with each other, and they just report what happened, and some of the combinations are good, others were not. So the first idea that they had is feature matching. So that means that basically it's going to change the loss that you're looking at. So instead of just computing a scalar and doing cross entropy of that, they're saying, yeah, but cross entropy has, there's a log term. The log term does not have very great gradients and things like that. And I want to have more more supervision, and supervision that's easier to backpropagate to and behaves better. So what they do is compute a vector for the real images and compute another vector for the fake images, and the discriminator is trying to make the difference large while the generator is trying to make it small. So they use this trick to transform your cross-entropy loss into an L2 loss. We're going to see a bunch of those in the future. All right, so mini-batch, they suggest mini-batch discrimination, which only makes sense if you if you combine it with the previous one, by the way. Because if I just put it like that, you're just thinking, yeah, that just means I'm going to use I'm gonna just use batching on my problem and compute everything on batches of size 32 as opposed to 1, which is what it is, but where it changes is that it changes the form of this thing, because instead of computing it of pairs of points, you're computing it on a sort of average of points that go through a tensor that combines all of it. But it's generally just a form of batching and saying, yeah, if I just look at one example, it's not going to be general enough, and it might give me an incentive that's not good for the general purpose. But if I look at a bunch of points, I'm going to get an average that's a better supervision. All right, third idea is historical averaging. This one is actually a bit simple. You remember that in the two-dimensional example with the video, there were oscillations, and the oscillatory problem was the entire reason why it was why the convergence was slow, and you'd intuitively, if you have less oscillations, you're gonna the convergence process is gonna be clearer and faster. So they just say, yeah, well, I'm gonna add a term that's gonna discourage your process to have oscillations. So they just take a moving average of what the parameters were, and they try to enforce that the parameters at the next step are going to be somewhere around the average before. So that's that's sort of like you see a specific problem that happens, you're putting Band-Aid on it. But it sort of works. Sometimes, not all the time. Right, label smoothing. I don't know if you may have heard of that before, because it's not at all restricted to GANs. So the idea behind label smoothing, if you're using cross entropy in particular, is you know that cross entropy is the KL divergence between two things, which are the distribution that you're generating, and the target distribution that's deterministic, where it's 1 for the real thing and 0 for the wrong thing. The problem with that is that you're pushing your network to generate this distribution, and because there is a softmax somewhere, you're pushing the logit to become plus infinity or minus infinity. And so that's regularization that's a little bit of a problem, because you're enforcing your weights to go sideways. So in label smoothing, you're just making your deterministic distribution a little bit less deterministic. So instead of being 0 and 1, it's going to be epsilon and 1 minus epsilon. And you're doing K on that. That's how transformer networks are trained, among other things. And they just think, yeah, I'm going to do that on GANs, and hopefully it's going to work. And it seems that it works, but only if you do a fake version of that, where you only smooth the real target, so the one, the logit, the one label becomes 1 minus epsilon, but the 0 for the fake remains 0. Don't ask me why. So that's what they call one-sided label smoothing. And now virtual batch normalization is just them thinking, I want to use batch norm on a GAN because batch norm is great and it regularizes everything. But batch norm, for some reason, doesn't seem to work if you apply it natively on a generator. I guess because it changes the output of the generator so much that your convergence process kind of get lost when you're in a two-player setting. And if you compute batch norm, if you compute your statistics on the batch that you're looking at, you're making every input that you generate completely dependent on the other inputs, and that generates all sorts of problems. So what they're saying is, I'm going to compute batch norm, but not on the data that I'm looking at, but on another part of the data. And I'm not going to move that part of the data. I'm just going to take a bunch of random samples from Z, and I'm never going to change them. I'm just going to look at what my network is doing on them and compute statistics on them, and use the statistics to normalize the rest of the data that I'm generating, which means at every iteration, you need two batches. You need the batch that you're using for training and the batch you use for the statistics. So it makes your training much longer. But apparently it works at least better than using batch norm. And I think that was the last one for this paper. Any questions so far? Those are going into we're starting a bunch of ideas that have something in common that are a new family. So if you have questions for what was before, might be the right moment. Otherwise, we can wait until the end too. So for the papers that are going to follow, if I recall, yeah. There's sort of like the idea of feature matching that we just saw. The whole reasoning process is I'm going to make the two-player objective with the coarse entropy is too complicated. I'm going to do whatever I can to remove that log term that makes all my gradients 0. and find a loss that's easier to get feedback from. So they use, let's say you want to use L2. A thing you can do is I'm going to try to fix a set of numbers and that are the targets, and you're trying to send the output. Let's say the generator is trying to generate outputs that go to a fixed A when you pass them to the generator, and there's a typo here. The discriminator, sorry, it's trying to minimize the loss, but by projecting oh my god, yeah, I should have changed that. So for the real data, forget the G that's here. The real data is projecting onto a B, and the fake data is projecting onto a C. So so your generator and your discriminator had these two objectives. If you just want the generator to produce real data, it would make sense that A is equal to C, which is what we have in the setting here. So that way, there is a point that means real and a point that means fake. And the generator is trying to send the fake onto real, and the discriminator is trying to send the fake onto fake and the real onto real. But that's not the only thing you can do, as it turns out. If the B is somewhere in if the C is somewhere in the middle between fake and real, it also works. And there are results as proving that if you're doing that, you're maximizing some sort of correlation between your two distributions if C is in the middle. It's an interesting paper. You can look it up. Yeah, this paper does something extremely simple which is kind of like the Dragon paper. They just want to add noise, but this time on the instances. So whenever you generate an image, you just add a bit of noise to it. When you get a real image for the discriminator, you add a bit of noise to it, and that is going to make the function the discriminator learns a little bit smoother, and the supervision throughout the process a little bit more effective. Extremely simple. You should try it because it's, in terms of code, it's basically free. And it's worth a shot. Yeah, we're going to get through the big one very soon. Energy-based GANs. Again, in I'm gonna simplify the problem family. This time, you're just pretty much ignoring the fact that you are trying to use the Jensen-Shannon divergence that we talked about last time, and you're basically just gonna solve a linear problem. So you just say the output of my discriminator is the only thing I'm gonna look at. There's basically no loss. You just add this thing so that it doesn't, there's no infinity term, and you're vaguely normalizing regularizing the process, but you just want to make whatever comes out of the discriminator big for real stuff and small for fake stuff. If you're the discriminator, and if you're generator, you're just trying to make this the output of the discriminator big, and that's all. And it's interesting. But we're going to see an even better version of that now. So Wasserstein GAN or Wasserstein GAN, I never know how to pronounce it. I'm going to say Wasserstein, but I might be wrong. So they are that's the one of the most the most radical simplification of GANs that you can do. But as it turns out, it's extremely theoretically grounded, much more than energy-based GANs that seemed a little out of the blue, maybe. So in the Wasserstein GAN is trying to solve the problem of the Earth-Muller distance, also called the Wasserstein distance, that we're gonna describe in the next slides. And in terms of optimization, they just look at the very, very simplified problem where you just take the real just put the real minus the fake, and the discriminator is trying to make that big, and the generator is just trying to make the fake small. So you don't even have the max, the positive part term that you had here. It's just real minus fake. Simple as that. But there's a catch, of course. The catch is if you don't want your, if you, in order for this not to become unstable and send everything to infinity, you need to constrain the discriminator to have a Lipschitz constraint of 1. So that might seem weird. We're gonna see how this is actually pretty theoretically grounded. So the Wasserstein distance, it's a divergence between two distributions that compute basically the cost of what you'd have to do if you wanted to transform one distribution to another. So it's, I think it's pretty much the most intuitive expression of divergence, especially if you compare it to the KL with its log term that seems to come out of nowhere, even though it's grounded in terms of entropy and information theory, etc. This makes a bit more sense. So that means, for example, if you had a distributions of products that are in warehouses in different parts of the country with different products that are in certain quantities in certain warehouses, and you had two of those, and you're just wondering, how do I transform the first into the second? For example, I have to take a bunch of stuff in Pittsburgh and move it to Cleveland, so I just take this number of stuff, I multiply it by 200 miles, and I add that to the term. But it's not at all, Wasserstein distance is intuitive in its expression, but it's extremely hard to compute, because to do that, you need a transport plan. So you need to know it's from Pittsburgh to Cleveland, because you might think, if I move some stuff from Pittsburgh to Columbus and then Columbus to Cleveland, it might have been a bit better. So in the most general setting, computing that distance is a sort of traveling salesman problem or something like that. And it's, in any case, it's definitely NP hard. But in simple cases, you can compute it analytically. So let's look at a simple example. So let's say you have two point masses. Do I have something to write? Yeah. So let's say this is your target distribution, and it's just 0 everywhere and 1 on 0. And you've got a bunch of, if you look at a bunch of different distributions that are the same thing, but instead of 0, it's theta. Now, from the perspective of the KL divergence, if you look at the KL divergence between these two, it's infinity unless theta is 0, and then it's 0. So why is that? It's because you have got this log term division term that just looks at the mass that's in common between the two distributions. So for example, if you've got two Gaussians that are like that, then under KL divergence, they are close because there's a ton of area in common under the curves. But if you were looking at two Gaussians that are extremely narrow but have pretty much nothing in common, they are extremely far apart. And the fact that the center of this is close to the center of that does not matter at all for KL. They only care about what's in the mass in common. So that's why for if you are looking at the setting of the deterministic thing, it's not differentiable in terms of theta. It's just infinity, and then it becomes immediately 0. Now, in the GANs, we are not looking at KL. We are looking at the Jensen-Shannon divergence, as we've said. In that case, it's not infinity that you get. It's log 4 here. And once you arrive here, it's 0. So it's better in a certain sense because the difference is smaller, but it is still not differentiable. So you don't have, in terms of GANs, you can interpret that as if your generated things are close to real, but still definitely not real, then they have no, you don't have any good feedback because you're not in the distribution, and if you're in the mass of the distribution, and if you're not in the mass of the distribution, for the divergence from the losses perspective, you're nowhere. You just you just in the infinity or in the log 4 area, so the feedback is the same, and you can kind of from this perspective you can see that as the reason why GANs have trouble converging. I hope it makes sense, at least at high level. The real math is in the WGAN paper, of course. Now, if you were in the Wasserstein example, well, it's simple. You need to move, if you want to go from this to there, you need to move all of the mass from here to here. So there's only one obvious optimal transport plan, and the distance, the Wasserstein distance, is theta. So it is completely differentiable. I'm just going to go a little further. Yeah. So this is kind of an illustration of Earth-Mother distance compared to JS distance, and why here you get useful gradients to go to the minimum, and here you do not. I'm just going to go a little bit behind. Now, the result they're using to argue that their definition of GANs is better is this result where it's been proven separately and in a way that had nothing to do with GANs that the Hofmuther distance can be computed using a dual method, sort of like in SVM if you ever had a machine learning course. I'm definitely not going to go into the details of this thing, but basically you need a supremum of a certain expression that involves a supremum over a function space, which is a little complicated, and you need to have the functions, the difference between the two functions be small enough, hence the smaller than a certain constant or upper bound function. So to transform that into a GAN objective, you can sort of see the relationship between the dual formulation and the loss that you had here, where you just take the difference of the expectation. Expectation is kind of like integral between the real case and the fake case, and you constrain that the Lipschitz of the discriminator is under 1. I'm not gonna mathematically say more on this on this side. Just gonna give some illustration of, so if you've got your two distributions, so here you've got the real at a certain time step and the fake at a certain time step, and if you're looking at a again, what a GAN discriminator would say is all over there you've got 0 gradients, over there you've got 0 gradients, and just in the middle where you're not, you have useful feedback. So you'd have a lot of trouble going from here to here using this, using the gradients that you get from this. But with the WGAN discriminator, that's now called a critic, not a discriminator, you have the same vocabulary in reinforcement learning, among other things. The critic is just a network that tells another network how to behave, but it doesn't have the binary background that you get in discriminator. The discriminator just tells real or fake, and here it does something a little bit different. But in any case, you can see that the critic goes kind of smoothly from one part to the other, and it's gonna provide a much more useful feedback. Now you may wonder, yeah, that looks way too good to be true. And you're right. Because you by transforming again into a WGAN, you sort of transferred the problem of how to optimize the GAN setting into the problem of how to optimize the critic under the constraints of the Lipschitz constants. And it turns out just computing the Lipschitz constant of a neural network is an extremely hard problem. Good luck if you try to compute it exactly. So the authors of the Wasserstein-GAN paper, what they do is they just solve a sort of upper bound problem on the Lipschitz thing. They say if I just clip my weights to be small enough, then if my activations are like this, I can just, at the very least, prove that my Lipschitz constant is not bigger than this. So if all my weights are 0.5, then my entire network is at least Lipschitz this. And they don't, they kind of like VAEs, they solve an upper bound of the problem instead of the problem itself. But as it turns out, this is way, way too loose of a bound, and it gets terrible results, which is why the Wasserstein-GAN paper has very good theory, but terrible results, as opposed to all of the other GAN papers. So someone once said that a lot of the best scientific ideas ever are lost in papers that were dismissed for having bad results. That might, fortunately, did not happen here. Wasserstein-GAN became a thing even if the results weren't good, because other people later gave better solutions to the Lipschitz problem. What time is it? Yeah. So here's an alternative where the setting is the same, but they just handle the Lipschitz part differently. So this is Wasserstein-GAN with gradient penalty. That's what it means. WGAN GP. So here, their version of constraining Lipschitz is instead of making the gradients smaller than this, like the quotient difference is smaller than this, I'm just gonna make all the gradients about 1 everywhere, and the gradient of 1 would mean of norm 1 would mean Lipschitz. So instead of making it small, I'm gonna try to make it exactly 1. So they just add this penalty term to the objective, where you get the penalty is bigger when the gradients are very different from 1. So the question is, where do you compute that? You don't compute it for the same reasons that we've mentioned in different papers. You don't compute it at the sample that you're looking at, but you compute it somewhere else that you randomly sample, but you cannot randomly sample on the entire space. So they argue that the best place to sample is in the area that's between the real and the fake distribution. So they take some linear interpolations between the real and the fake data, and that gives you the region where you want your Lipschitz, your gradient norm to be 1, and which means you keep the discriminator smooth in the area where you want to go. All makes a lot of sense, I think. So we can get a bit of visualization of default WGANs with this version of WGANs. So you can see the target distribution in yellow, and what the GAN is, the values of the critics in different areas of the plan. So you can see that if you clip the gradients of the discriminator, you get stuff that is locally linear. It's your entire function is a bunch of segments that are just concatenated with each other, and it gives you weird squares like this, even though you are trying to produce points or spirals. So here, for example, you try to approximate a spiral with a square, which isn't great, while the WGAN critic gets something that's significantly better. You get much closer intuitively to a spiral here and much closer to a point here. Yeah, spectral normalized GANs sort of have an alternative way of solving the Lipschitz problem. So they also solve a bound like the original paper, but a better bound. Because if you're looking at the Lipschitz constant of a matrix multiplication, that's not just, you don't have to compute something for the weights independently. You look at what the weights do together as a linear function. And so you're just trying to maximize the upper bound of this thing, like how much can the matrix change the distance of a vector, which roughly gives you the maximal eigenvalue. Kind of depends whether the matrix is symmetric or not, which is not, but no, maybe it's a singular value probably. I don't remember, but in any case, you can compute this quantity, and by trying to, you can constrain each layer to have this quantity smaller than what you want by clipping, and doing that gives you something that's at least better than the clipping version, WGAN. Fisher GAN takes a different approach of the problem, where you say instead of constraining the discriminators and the networks, I'm going to constrain the loss. So it sort of ends up at the same result in a way. I don't think it works as well. You can, but it's been proposed. You just normalize the term of the loss by its to make it always 1 in a sense, and you're gonna backpropagate on this instead of just on the upper term. You can see that compared to the problem here, where you were sampling somewhere else than where you're looking, the points you are looking at. Here, you're just using the same values that are here to regularize, which gets you back to the same problems that we mentioned before, where your distribution kind of becomes a peak around the real data and things like that. So I guess that's one, you can see that as one of the reasons behind the problems that Fisher can get to. But at the very least, you know that it exists. Finally, you remember lab GANs that we mentioned last time, where you just take a chain of GANs that go from generating something small, and then you put that as the conditional input of another GAN, and you generate something bigger, and you get sharper and sharper results. I'm just putting them back here because they're sort of related to the next thing we're going to see, which is called prog GANs, where it kind of does the same thing, where you're gonna expand the network slowly and iteratively, but this time the way they do it is add different layers to both of your networks. So like, for example, you start with a GAN that your GAN is just taking random samples, and with this convolutional layer, you get an image that's 4x4, and then you add a different, once this is trained, you add a different layer that makes that into 8x8, and you just do this process iteratively. Not really related to what was there before, but it's an interesting idea that you may have had, so you can just, if you think it makes sense for your project, you can just look it up. So yeah, you can just get a better idea of what it's doing with the figure. Yeah, I don't have much time, so I'm just gonna not spend too much time on this and just go directly to the takeaways so that you can get to ask a bit of questions. So we've mentioned a bunch of ideas. The trick, the trap that you must not fall into is think this idea that I've seen definitely solves my problem, because the GAN problem is complicated whether you like it or not, and you sometimes if you take the right approach to, for example, an MP problem, you fall into the specific case where you can solve this problem, but nothing tells you that you're in this case. So it's very possible that you try WGAN, it's not going to work for you specifically. I just gave you the intuition that's behind the network. I didn't give you the papers that might have argued differently, but you've got a ton of literature on the subject. And just remember that generally every method, if it looks good, probably has a catch. So the catch of this kind of methods is that you're transforming a problem into another that's also difficult. The catch of the methods like unrolling are that they're extremely computationally expensive. Because if you remember, you have to backpropagate into something that's much, much deeper if you unroll. And so maybe your GPU might just explode if you do that. You got a bunch of methods that are based on sampling, so you can never be sure if what's going to happen is going to be repeatable or not. And you've got a bunch of methods that are based on bounds that make your problem easier, but also less further to the real problem. And so you're solving something that's easier, but the results are going to be worse. So yeah, a lot of bad things can happen with those. But it's worth checking them. I would argue if you have a problem with a GAN, try a regular GAN first and then a WGAN probably. That seems like a good trend in general. So if you just sum up in terms of families of partial solutions, you got the family where you try to regularize the discriminator to make the thing easier to optimize. You have the consensus idea where you try to make the two players work together toward a common goal instead of just doing their own thing and in a greedy way. You've got the entire WGAN, energy-based GAN thing, where you simplify the loss or the networks to a very large extent. You got the methods that constrain the complexity of the discriminator, hoping that it's going to solve your problem. But again, what's the complexity of a neural network? It's hard to put a word on that. It's an open problem with a lot of literature on the topic. And you can try to chain together GANs so that each solve an easier problem than the original one in the sort of curriculum learning kind of fashion. So as for the current research, well, it's you use the most expensive ones and you put a ton of GPU on the on the problem, and it seems like not a super satisfying thing to do, but you can't argue with the results, to be honest. They're just getting better and better. It works on images, it works on everything. Now models are extremely large, extremely scalable. People know how to parallelize all of these things. Push the limit further and further. Deepfakes are going to ruin democracy, etc. Yeah, just final slide to go back on the idea of perceptual loss that I mentioned last time. So you know that neural networks are universal function approximators, and you know that loss functions are functions. So behind GANs, there is the idea that just make your modelize your loss with a neural network, and you're gonna get something good. And now you know what are the good things and the bad things behind this entire idea. And yeah, that's pretty much it. Do you have any questions on today's lecture? Well, and with that case, I guess we can call it an end, and you'll see VAs later, and you'll see that they do the same thing, but in a more theoretical way and less good. I think it's for Monday. All right, goodbye.